Good afternoon, everybody. I'm sure you're still awake after a long day. So I'm now going to start actually with the academic session, which meant to start at 5 o'clock. But obviously, as the last session is always a session that has been least appreciated. But obviously, the academia is keen, and academia is here to build the future skill sets and research. I would really greatly appreciate if you would support the PhD student, grad students who are going to give a presentation today, and give them also encouragement, give them directions. So the process, what we have here is we have a number of presenters. They have been given 5 minutes to give a presentation, 3 slides. So the process is every academic here, academic staff or PhD student or grad students will give a 5 minutes presentation. Each of them have also a poster. We have put it up to next door. So what they're going to do is they're going to introduce their research, what they're interested in, and what they want to do. And next room, they have some slide, poster where they introduce their research more in details. So it gives you an opportunity to know the individuals here during his presentation and maybe engage in discussion during the reception next door after this 5 minutes presentation by each academic staff. So our first presenter is Madeleine Glick. Dr. Madeleine Glick is currently at University of Arizona College of Optical Science. She's previously worked at Marconi, Intel, and optical device and optical switch for computing network. And she's industrial liaison for NSF Engineering Research Center and research associate at ONF. Madeleine?
Okay, good afternoon. I think I'm first because it's probably the most different from anything that's come on before or after. My name is Madeleine Glick. I'm here to talk about our work on machine learning-based adaptive flow classification for optically interconnected data centers. So I'm representing our group, which is Human Rastegarfar and Mingwei Yang and John Wissinger, and we're working with Nick Viljan here from Metronome Systems. So just as a brief overview, we're looking at how to, do we have a pointer or something? So we're looking at hybrid optical electrical networks, and the idea is how can we overcome some of the problems that optics has in terms of slow configuration time for the MEMS switches, and we want to enable flexible high bandwidth shaping for load balancing. So my background is photonics and optical networks, and this is one specific problem, but I just want to say that we know that optics is good for high bandwidth transmission, but when it comes to processing, it's not very good except maybe in some research labs. So this is where the edge intelligence that the Metronome NICs give us can really open a lot of opportunities. I think that would solve it would enable a lot of optical interconnection networks and computer systems. So what we've done here with NIC is we have a neural network-based system to predict hotspots in the data centers, looking for elephant detection. And the neural network allows us to detect large, long-lived flows far quicker and more accurately than leading heuristics. We've looked at some traffic from the university, and we were able to classify 50% more accurately than leading heuristics. We were able to get 75% of the elephants as opposed to 50%. And we also, Human is working on simulation, so we want to extend it to larger networks. And that indicates that this design can improve the hybrid multi-tenant data center utilization by around 2.5%, 2.5 times. We have more on our poster, but like I said, we're looking at a hybrid optical electrical network. So we have servers, the optical switch, electrical switch, and the figure indicates the issue about identifying the elephants, mice, and what we call hares and tortoises. So the idea is that a hare is a high bandwidth bursty flow that often gets mistaken for an elephant, and if you put that on your optical link, high bandwidth optical link, it doesn't give you as good performance. Okay, so in terms of the implementation, at the University of Arizona, we're building a mini data center that will have an intelligent SDN control, and that will fit into situations where the NFP is being used for OVS. Our experimental implementation is being designed in collaboration with Netronome, so we're designing it so that we have the servers and the NFP NICs from Netronome. The experiment and the research is enabled by the NFP. The idea is to have a pool of computational resource on the edge that allows us to implement the added functionality without hamstringing the CPU. So, the idea is we use the edge intelligence to enable the optical network to have better performance. And Netronome is assisting us by, so we're the optical experts, they're the data and control plane neural network experts. So we're building this together because I strongly believe that you can only solve a lot of these problems by doing interdisciplinary work, and interdisciplinary work has to be done together. Netronome were also assisting us in gaining extra funding, so they became a member of CYAN, which is our NSF-supported research collaboration. There are about 10 universities, USC, San Diego, UCLA, Columbia, and Netronome is an industry member of that collaboration. We're also doing proposals together. And our expected outcome is to have our long-term aim is to build a virtualized, adaptively intelligent, multi-tenant, multi-application data center that can use AI to dynamically load balance the pool of virtual bandwidth and detect anomalies for inspection and optimize power consumption. So this is really important for the optical networks, so come talk to us at the poster, and that's it for me.
Our next speaker is Anthony Kaufman. Anthony is second-year PhD student at University of Washington, working with Tom Anderson, Arvind Krishnamurthy, currently working on project evaluating performance benefits of NIC model with limited match action and processing.
Okay, thank you. Okay, yeah, as said, I'm working with those folks back at UW. I also wanted to mention Simon Peter, who is currently a postdoc, but who is now moving as a faculty member to UT Austin. So basically the goal of this project is basically to figure out, so on one hand, Netronome has this fully programmable model for a NIC. On the other extreme, as shown like in the earlier talks, you have NICs that just have like this fixed functionality. And in like kind of the medium time frame, there's not going to be like the sudden shift where we move from to a scenario where basically every server in a data center has a fully programmable NIC. So we wanted to look at kind of a model that's in between and figure out kind of how far that will get us in terms of performance. So the model we assume here is basically that you will have some limited match action type functionality in the NIC. And one important factor we also included is that this match action processing will be integrated with the DMA engine. So you can actually have some additional control over how, like what the DMA interface for the NIC looks like to the application and the host in general. So you're not necessarily limited to just descriptor queues. And so basically, this paper, we submitted this to ASPLOS, and we just got the notification that it was accepted. And we did an evaluation of a set of applications in terms of the performance benefits this model has on just the host side. So one caveat is we didn't have access to a programmable NIC to like get the full system perspective on these improvements. So basically what we ended up doing for all of those is emulating the NIC functionality in software. So the emulation for the different use cases is slightly different. But basically the idea was to get, from the application point of view, get as close as we can to what would happen if we had such a NIC. So we looked at 3 major use cases here. So first one was a key value store. The high-level idea there was basically to have the NIC steer packets to the right core based on a key, so that there would be some locality there. So we don't have a lock contention and cache coherency overheads because like all the cores are accessing the same keys, etc. Also there we looked at a slightly customized DMA interface. So instead of the NIC just throwing packets up at the application, the NIC, what we ended up doing is that the NIC would stream especially write requests to the key value store into just one big buffer, which simplifies two things. So basically the key value store can simplify its own buffer management, and also it simplifies processing in general, because you're just kind of streaming over those, and you can, more importantly, you can leave your write requests there, and you don't have to copy from packet buffers into their final, like your key value buffers. The second workload we looked at is Apache Storm, which is a kind of real-time analytics system where you get some tuples and you process them through a graph, processing graph, and you try to, so the two things you're looking at there is you get your data at very high, you can get your data in very high quantities, so there's obviously a throughput you're interested in, but you also need to get answers out of the system within some reasonable response time. So you also care about latency. And there again, we basically did some packet steering to improve locality in the processing core, as well as some protocol offloads to simplify the processing on the worker cores. So for instance, the worker cores don't have to deal with sending back acknowledgements for flow control, etc. And for the third workload, we looked at Snort and scaling that up to higher bandwidth. So Snort does deep packet inspection. The way this is currently parallelized is basically you just fire up a Snort instance on multiple cores and have the NIC distribute packets to those. You can just, one way of doing this is just doing this randomly. But like Snort has a fairly large working set in terms of state it uses to figure out which flows are potentially harmful, etc. So if the NIC can actually classify those packets into kind of buckets that will enable the individual worker cores only to having to look at the subset of their matching criteria, the cache footprint of the whole thing is significantly smaller. And like in all of those, we saw throughput improvements from between like 1.5x and 2x, and as well as latency improvements up to 40%. So future directions. So one of the obvious next step is to evaluate this with an actual full system implementation. So the metronome NICs would be very helpful for us to at least get like the full system working with this, where there's PCI in between, etc., not just some emulation sitting in software somewhere. And there's also the next kind of bigger question we are currently looking at is if you have this model where you can modify the DMA interface that the NIC presents to the application, how does the application programmer actually deal with this? Like for us, we just went in there and like modified every single application and got our hands really dirty with the details, but that's obviously not going to work for like the general data center applications. So yeah, we're trying, that's well, like the one big open question we are currently looking at. And yes, if you have questions, please come talk to me at the poster afterwards. Thank you.
Our next speaker is from University of Quebec and Montreal. Khalil Bleich is a graduate student in computer science at University of Quebec and the research assistant in LTIR laboratory, focusing on research and development of network systems, especially network virtualization.
Actually, hi everybody. First of all, I would like to thank Netronome for their invitation. And so I will present to you an SDN-based platform for unified data plane. But before, let me highlight some some of our research directions. So through our work, we address some problems regarding virtualization, hardware abstraction, resource management, and packet processing. So we have developed in different platforms such as EasyChip NP4, Netronome NFP 3000 series, and Calgai many cores, TK, Intel CPUs, and we in our development we use DPDK, ODP API, and some of vendors SDK. Actually, I will just list to you some of our work that we did recently. So we implemented the 100 gigabits OpenFlow 1.1 switch over a network processor, the EasyChip NP4. We developed a tool to configure network devices, and we developed recently a network-aware hypervisor that manage different virtual switches over a network processor. We did this abstraction to two kind of network processor, which is Netronome NFP and the EasyChip NP4. Then we proposed some kind of data path acceleration using TKM and network accelerators, and in 2015 we proposed we worked with our industrial partner, which is Ericsson, on developing a packet forwarding rules compiler for switch pipeline architecture. So for the idea behind the SDN based platform for unified data plane, it was motivated by our recent experience in developing in using different platforms. So it is motivated by the fast evolving of network virtualization. Actually, network devices are shared between different instances. So the idea is to abstract the underlying hardware resources while providing flexibility and programmability. The idea is to handle different packet processing instances to handle different type of loading. So this project aims to provide an optimal task packet processing to task to resources mapping. We will delighted to discuss with you some of this the details of this project during the poster session.
Our next two speakers are from California, University of California, Davis. Our first speaker is Cheng Liu. Cheng is a PhD student at University of California, Davis, working with Professor Chen-Ni Chua on SDN measurement and security.
So hello everyone, my name is Chang from UC Davis. So I will briefly talk about the project that I'm going to present today, and more information is available in the poster. So the topic of the project I'm going to present is network inference with SDN-based online learning. So in this project, we revisit the network measurement problem in the context of SDN-based networks. So with SDN, it is possible that you can adaptively decide what kind of flows you are going to observe and at what kind of granularity, and based on the online learning results you obtained. And with the global view of the SDN controller, that it is possible for you to globally optimize the measurement resource allocation, means that globally decide which switch to measure what. So in this study, we used the TME, which is traffic matrix estimation, as a case study, and show the performance for heavy hitter and hierarchical heavy hitter detection. So for the proposal for Netronome, so the first thing we want to exploit is the performance of network flow processor in handling large flow rates and the complex measurement tasks. And the second thing we want to see is how to use the flexibility of network flow processor in multi-round statistics gathering for HH detection. So, basically that's it.
Also, our next speaker is from University of California, Davis. It is Arun Agurami. He's a PhD student, also with Professor Cheng Ni Jua on network security topics and measurement.
Hello everyone, I'm Arun and I'm from the RubyNet lab at UC Davis. My work is about uncovering malicious traffic footprints in cellular data networks. Increasingly nowadays you see in the papers that there are security threats affecting every large organization and a lot of consumers are being affected. And in this particular study we take data from an operational cellular network and we perform measurements to actually understand what's going on in these networks. And our idea is that we can develop some cross-layer threat detection techniques as an alternative to conventional detection methods, which may involve application layer payload and so on. And in this paper, we specifically show that we can use some network statistical features which are based on packet counts, byte counts, entropies, and so on, and use these features in a machine learning model to effectively detect malicious domains. And the way to do this, in order to achieve this, we use large data sets from actual networks, maybe cellular networks and Wi-Fi networks. And we have a paper on this in this year's PAN conference. We have more details about this in our poster. As for the proposal, we would like to see if we can adapt some of the methods we have developed to the SDN paradigm. And specifically, if we can offload some of these detection techniques to the network flow processor so that we can improve security of the whole system. And as an overall goal, we want to see if we can adaptively coordinate these detections at various points in the network. Thank you.
Now, this is our last speaker, and it is Sivarasma Krishnan. Sivarasma Krishnan is a graduate student at University of South California. He is part of the Network System Lab and is advised by Jelena Majkrovic and Minlan Yu.
So I have a big name. It's actually Sivaramakrishnan. You can call me Shivram. I'm a student at the University of Southern California, advised by Minlan Yu and Professor Jelena Majkrovic. So today I'm going to be talking about how the Netronome INIC cards can be used with our research. So let me get started. So what is a DDoS project? So there has been an increase in the cyber attack in the recent past. So reports say that DDoS alone has increased by about 400% in the last year alone. So there has been enough funding for cybersecurity research, and the solutions which are actually given are kind of reactive to the attacks which are being generated. We are never able to be proactive and outsmart the attackers. Probably one of the reasons for this deficiency could be, say, the lack of experimentation test beds. So to address this shortcoming, the US NSF has been funding the DDoS project since 2004. So the DDoS project consists of about, it's an operational testbed facility for cybersecurity research, test, and evaluation. It actually consists of about 500 general purpose computers, which are actually hosted at USC and at UC Berkeley. And any member or any researcher can actually become a member of this DDoS project after a very simple screening, and he's actually given complete flexibility. Of course, the total number of machines which are allocated per user is limited, but you can do a lot of it. So every member can actually choose, set up any topology, run any operating system, run applications, and do whatever he wants to. So this has been extremely useful in the research community, as they could actually test and evaluate their experiments in realistic conditions. Also, it has been extremely useful in academics as well, as there are more than 100 distinct classes and in over 67 institutes around the world who have actually used DDoS. So now I'm going to talk about something which we have been working on in the past year. So we are trying to reduce the total number of DDoS and BGP prefix hijacking attack, which has been happening all along. Now, the defenses which have actually been employed today either work in isolation, or even if they do work in collaboration, what happens is that they require a change in the router infrastructure, or sometimes they actually require to be implemented in a large scale to be effective. Now, there is no framework to actually engage multiple ISPs to help the victim out. But imagine a situation if a victim is under an attack and the victim could query any ISP who's willing to help to actually save or preserve its legitimate traffic and bring down the attack traffic. So this is where Sense comes into picture. I mean, actually I had a video, but it's a PDF, so you can't play videos. So Sense allows the victim to actually query any ISP to help them out. So it actually brings out the principles of SDN to help the victim. For example, suppose there's an attacker who's actually attacking the victim. The victim could actually send out traffic queries to the Sense server, and the Sense server would actually give back statistics on a particular query. Say the victim could actually query on a particular IP prefix, and it will return the stats. And the victim could actually also request to filter out the particular attack traffic or change the AS path or demote a particular AS path. So there's a lot of flexibility which is actually given to the victim to preserve its legitimate traffic and to reduce the attack traffic. Now, Sense is one of the many SDN security-related research which is actually going on at USC. Now, innovations are which actually work on extremely predictable environment is not effective. But unfortunately, Ditto Lab doesn't support SDN, and we are looking forward to move Ditto to make sure that it supports SDN. So there are two approaches. One thing is that we could actually buy switches which actually support SDN, or we could actually use Netronom's iNIC and replace our NIC cards with their iNIC and support SDN. So this is my presentation. You could come talk to me in the other room if you guys are interested. Thank you.
Okay, we also have another poster, but no presentation, so I would like to introduce the PhD student. It is from Carnegie Mellon University in Pittsburgh, Antonis Manosis. Antonis is a first-year PhD student in Carnegie Mellon University in Pittsburgh, advised by Professor Viyash Shekhar. His research interests focus on network and security, and his current projects are in the area of network monitoring. He has a poster, so he doesn't have a presentation, so I would encourage you to basically engage during the reception. Thank you very much for the support that you have provided for the academic presentation, and join me to basically thank the academic presenters again. So I will call Bobby for his final statement before we close down for today.
Thank you, Professor Cesar. Very nicely done. Thank you. I hope everything everybody said comes true and everybody produces lots of code for the process. The company has put in a huge amount of effort into making a lot of material available to the research community. Honestly, from here on, I'm hoping that there's pull from the people in this room. And as you can see, the company has plenty of really talented engineers who are very interested in engaging at a deep level. So please use the material, download it, interact with the company, and contribute back to the community. And in closing, if we could thank our instructors, I think they did a wonderful job for 8 hours today. So if you guys could stand up, all the gray shirts, stand up, and thank you. And we're done. Thank you.